Hello my dear friends, welcome to our channel. So in this lecture, we are going to discuss about kinematics. Kinematics, it is a branch of the physics. It is a branch of the physics and mechanics in which we will discuss about the objects which is in motion but without the reference of the force, without considering the force acting upon that object. It's only known as kinematics. So, as I told, we will not consider the force acting upon the object, right? We will only consider the motion. So whenever, for example, if I am taking a car, if it is in motion, for example, that means this car is going to move with some velocity. I am considering it as u, right? After some time, as it is in the motion, definitely this car would have covered some distance. As you can see here, this car is covered some distance. So the velocity after a time t is going to vary. Why I am saying after a time t the velocity is going to vary? Because in the car there will be accelerator. So whenever you are pressing the accelerator, your velocity will change. As the velocity is changing, that means acceleration is present. Right? The accelerator works. What it will do? It changes the velocity of the car. Whenever it will accelerate, definitely your car will get speed up. Your velocity changes. Initially it is 5 meters per second, but when you are accelerating the car, it will go to 7 meters per second. That means my velocity is changing due to the acceleration of the car, and it is also covering some distance. So whenever an object is in motion, whenever a body is in motion, we will see these 4 parameters. What are those 4 parameters? Here at a time t seconds, what it will do? That means at a time t, the velocity is going to be changed. The position of the body is going to be changed. Right? At a time t, the position of the body is also going to be changed along with the velocity of the body. So four parameters are important in the motion. Whenever an object in the motion, you can see velocity is important. Why I am saying velocity is important? Definitely if acceleration is present in a car, then definitely my velocity is going to vary time to time. As the time is changing, my velocity is also going to change. As my velocity is changing, I am covering some distance. If the velocity is 5 meters per second, that means per second this car is covering 5 meters. That means if 1 second is finishing off, that means my car is displaced by a position of 5 meters. That means it is moved to a distance of 5 meters from this position to this position within a second. Right? So whenever an object is in motion, these 4 parameters are important. The time will come into the consideration along with the velocity, position, that means the displacement of the body, and then acceleration. What will happen if my velocity is constant? If here to 5 meters per second and here to my velocity is 5 meters per second, after a time t seconds, it indicates that my velocity is constant. My velocity is not changing as the time is changing. That means I am not accelerating my car. That means I am not giving any acceleration to the car. When I will say that I am accelerating, whenever I am accelerating the car, you will see the change in the velocity. You will see something like needle that will reflect like this. As you are accelerating from 20 km per hour to 40 km per hour, as you are accelerating, you can see in that one, the pin will show you. Right? Like the same, if you're not accelerating, if you're moving with the same velocity, that means the car is not having any acceleration right now. within these seconds, within a time t, there is no acceleration and my velocity is constant. That means my acceleration is 0. When my acceleration will be 0? When the velocity is constant. If the velocity is constant, then my acceleration is going to be 0. So in the kinematics, as we are going to study about the motion of the body, these 4 parameters are very important. What are those 4 parameters? Acceleration, displacement, velocity and time. These 4 parameters are very, very important in kinematics, because we are going to study about the motion of the objects and we are not going to consider any force upon it. Right? So these 4 parameters are important. So I'm now just going to take you the kinematic equations. What are kinematic equations? What I'm going to do in the kinematic equations is that I'm going to make this acceleration is constant. I'm going to make this acceleration constant. If I'm making this acceleration constant, if the acceleration is constant, that means my 3 variables, my 3 parameters which is present here will change. I'm just keeping my acceleration constant. If I'm accelerating the vehicle, I'm just keeping at the same accelerator. I'm just keeping at the same acceleration. I'm not changing the acceleration. But as I'm keeping the same acceleration, as acceleration is present, my velocity is going to vary time to time. As my velocity is changing to time, my acceleration is there. Is that the variable acceleration or the same acceleration? I am considering my acceleration as the same. That is why I wrote here, I am considering acceleration is equal to constant. That means same acceleration throughout my travel. Right? Throughout my travel, it is going to be the same acceleration. So now acceleration is constant. 3 variables are there which is going to be changed. Right? So with the help of these 3 variables, we are going to derive kinematic equations. So with the help of displacement and time relation, we will derive one equation. With the help of velocity and time, we will derive one equation. And with the help of displacement and velocity, we will derive one equation. So there are 4 kinematic equations, and now we are going to derive those kinematic equations in this lecture. So I am starting with the first one. What I am considering, my acceleration is going to be constant throughout my travel, throughout my motion, my acceleration is going to be constant. If you want an example, you can see here. If here a ball is present, I'm just holding a ball. I'm here holding my marker. Whenever I'm leaving this marker is falling down. And it really also fallen down here. Yeah. So whenever I'm leaving this object, it is going to be fall down. So why it is falling down? Once if I'm removing my hands, the gravity is pulling this marker. But as I'm holding this marker is not falling down. But once I'm leaving my marker, it is falling down because the gravity is pulling this one. So here this ball, as I'm leaving this ball is going to go down and going to strike the earth or going to strike the surface. Why it is happening so? Because in the downward direction there will be an acceleration due to gravity, which is nothing but g. It is the acceleration due to gravity, and it is constant. 9.8 meter per second square. So acceleration due to gravity is constant for everything. If I am leaving this object, whenever I will leave, here the gravity is pulling in the downward direction. The marker is experiencing the acceleration in the downward direction because the gravity is trying to pull down. As it is trying to pull down, the acceleration due to gravity in the downward direction is equal to 9.8 meter per second square. If I am not having this marker, instead of marker I am having a ball. If I am leaving that ball, so that ball is also going to experience the same acceleration due to gravity, 9.8 meter per second square. So for every object, for every body in the vacuum medium where there will be no resistance, my acceleration is going to be same, my acceleration is going to be constant, and it is 9.8 meter per second square. And you can see here, as the acceleration is constant. So what will happen when my acceleration will be constant at a time t is equal to 0 second, my object or my body will have some initial velocity, and it will have some initial position, whenever my time is changing, that means at a time t seconds, it is going to be changed as v, and it is going to be changed as st. My position is going to be changed after a time t seconds. Right? So it is what the variable is going to change. After a time is changing. As the time is changing, my velocity is going to be changed. As the time is changing, my position is going to be changed. As the time is changing, even though my time is changing, my acceleration due to gravity is going to be same, is going to be constant. Right? So now these three variables are going to change, and by having these three variables, we are going to derive the kinematic equations right now. So I am rubbing these things. Yeah. So I am having three parameters. What are those three parameters? Acceleration is constant. I am writing here acceleration is constant. I am having four variables: acceleration, velocity, displacement, and time. So as acceleration is constant, I am removing this one. I am having three parameters. From these three parameters, I am going to derive the kinematic equations. So here, for first one, we should have to take velocity versus displacement. We should have to find the relation between the velocity and the displacement. So as you can see here, no. Okay, velocity and displacement, we should have to derive the relation between the velocity and displacement, velocity and time, and displacement and time. Here we should have to derive in three relations. First one is velocity versus displacement, and then we should have to find the relation between velocity and time, and then we should have to find the relation between displacement and time. I am going to find the relation between velocity and time first. I am going to find the relation between velocity and time. Relation. Okay. I am going to find the relation between velocity and time. How I am going to derive the equation for the velocity and time? Is there any formula? Because my acceleration is constant, I am having velocity and I am having time. Is there any formula in which these three variables, these three parameters will be there? Yes, there is a formula which is known as acceleration. And what is the formula for the acceleration? Change in velocity upon change in time. Change in velocity upon change in time. What? So here, as you can see, change in velocity upon change in time is nothing but acceleration. We are finding the relation between the velocity and time, and my acceleration is constant. You can see here, I am taking these three parameters and I am having a formula for it. Acceleration is equal to change in velocity upon change in time. But what I said is that as my time is changing, my time is changing, my velocity is going to be changed. Right? So here v2 minus v1 upon t2 minus t1. But if the time tends to 0, that means it is going to be nearly 0. For example, if I am asking you, say me what is the acceleration, tell me what is the acceleration at a time t is equal to 2 seconds. I am asking you exactly say me what is the acceleration at the time t is equal to 2 seconds. Then definitely there will be some minor difference in the time. Right? So at that time, what is the acceleration we should have to find? At that particular instant, we should have to find what is the acceleration. That means my time is nearly going to be tending to be 0. It is going to be 0. There will be no difference. My time is going to be 0, is tending to be 0. Right? Why I'm saying it is tending to be 0? I'm asking exactly at an instant, at t is equal to 2 seconds, say me at t is equal to 2 seconds, what is the acceleration? How will you say? That means my time is nearly tending to 0. I'm asking exactly at that time, say me the acceleration. Tell me the acceleration. Then at that time, my time is tending to be 0, my delta t is tending to be 0, then acceleration is equal to, if the limit time t tends to 0, then we will call this del v upon del t as dv upon dt. It is the instantaneous acceleration. It is the instantaneous acceleration. At an instant, at a particular second, if someone is asking us to find out the acceleration, then we should have to use the formula acceleration is equal to dv upon dt. Acceleration is equal to dv upon dt. You should have to remember this. So here limit t tends to 0, del v upon del t is nothing but dv upon dt. So I am writing here acceleration is equal to dv upon dt. So acceleration is equal to dv upon dt. What I am going to do is that now I am just going to bring this dt here. So a into dt is equal to dv. Right? Now I am writing like this. dv is equal to a dot dt. I am bringing this dt here. So a dot dt is equal to dv. Now I am going to integrate this one. Right? So whenever I am going to integrate this one, see here the initial velocity is u, final velocity is v. So when my time t is equal to 0, I will have some initial velocity, I will have some displacement. When my time t is equal to t, I will have some final velocity, I will have some displacement after a time t. So here it is 0 and here it is time t. So what is the integration of dv? Integration of dv is nothing but v. V. How I am saying integration of dv is v? Everybody knows this one. Integration of x power n is equal to x power n plus 1 upon n plus 1. It is the formula for the integration of x power n. Here it is integration of dv. Here it is integration of dv. As it is integration of dv, what I am doing is that, you can see here, I am just writing here v power 0 into dv. Is there anything wrong? Anything power 0 is nothing but 1. That means 1 into dv. Anything power 1 is nothing but 1. Anything power 0 is nothing but 1. 1 dot dv is nothing but dv. That means whatever I wrote here is absolutely correct. So I am just going to apply the formula here. So v 0 plus 1 upon 0 plus 1. Right? I am just integrating this one. V 0 plus 1 by 0 plus 1. So v power 1 by 1. So I am writing here the integration of dv as v, and I also taught you how to derive the integration of dv, and I also taught you in which way I am saying that my integral of dv is nothing but v. Right? So you can see here, what is the upper limit and lower limit? It is the lower limit and it is the upper limit. So instead of v, I should have to substitute first upper limit minus the lower limit. If you know the integration, then it will be more easier. If you don't know also, it is nothing to worry about this one. So here, I am just writing here integral of a. A is constant. Whenever something is under the integration and it is constant, then we can remove that one from the integration and we should have to write outside of the integration. Right? I am writing the acceleration outside of the integration. So integration of 0 to t dt. And what is the integration of 0 to t dt? So here you can see here it is dt. So for the dt also I am writing t power 0. Then I will get as t. So integral of dt is nothing but t 0 to lower limit. It is the upper limit and it is the acceleration. Right? You can see here. I am writing here now. It is the v. See here. It is upper limit minus lower limit. What is upper limit? Here upper limit is v minus lower limit is u. So v minus u. I'm writing here v minus u is equal to a upper limit minus lower limit t minus 0. So v minus u is equal to a into t. V minus u is equal to a into t. So v is equal to u plus at. So you can see here I am having the velocity, acceleration and time, and I got an equation here. V is equal to u plus at. It is the relation between the velocity and time when my acceleration is going to be constant. When my acceleration is going to be constant, it is a relation between the velocity and the time. So v is equal to u plus at. Now I am going to see the second relation. What is the second relation? Between displacement and time. Between displacement and time. Is there any formula for the displacement and time relation? Displacement and time relation. I already found the formula for the velocity. V is equal to u plus at. V is equal to u plus at. So I am having a formula for the velocity. What is the formula for the velocity? V is equal to del s upon del t. Change in the position of the body upon change in the time. So whenever my del t is going to be 0, is tending to be 0, that means at the time t, at a particular instant, if I am asking you the velocity, for example, at the time t is equal to 2 seconds, tell me the velocity of the car. So am I asking you exactly at that time, at that particular instant, tell me the velocity. At that particular instant, I am asking you to tell me the velocity. Right? For that, we should have to use the differentiation. So instead of del s, I am going to use, first I should have to write here limit del t tends to 0, then del s upon del t. Then in this format, we should have to write ds upon dt. So v is equal to ds upon dt. Next step, what I am going to do is that I am keeping my ds here and I am bringing this dt here. So ds is equal to v dot dt. I am going to integrate these two. And what is the position? Initially s is equal to 0 meter. Definitely if my object is here, it is not yet started, my car is not yet moving. That means it is 0. It is at 0 meter. Right? It is not yet started. It is at the rest state. Right? So whenever it is moving, it is going to cover some distance. For example, 5 meter in 1 second. Right? So it will cover some distance. I am considering it as s, and it is dt. So whenever my position will be 0, whenever I am not moving, at that time my t will be equal to 0. After some time, my object or my body will cover some distance, and that is nothing but yes. We should have to substitute the limits like this. And then what is the integration of ds? Integration of dt is d. Integration of dv is v. Integration of ds is s. What is the lower limit? 0. Upper limit is s, is equal to integral of 0 to t. What is the v value we found in the previous equation? V is equal to u plus at. U plus at. Right. So I am writing here u plus at into dt. Right. What I am going to do is that here it is s. That means it is s minus 0. S minus 0. How I wrote s minus 0? Upper limit minus lower limit is equal to, here you can see I am having in addition form. If you don't know the integration, I am just going to segregate these two into two parts. I am just going to segregate these two into two parts. See how I am segregating here. I think I will segregate here. No problem. I will segregate here. Then it is upper limit minus lower limit. S minus 0 is equal to integration of 0 to t. It is u into dt. U into dt plus, once again we should have to integrate 0 to t and then at into dt. At into dt. So whatever the function which is present first, we shall have to integrate that one with respect to dt, and then whatever the function which is present second, we shall have to integrate that with respect to dt. And I wrote here that one. See here, u into dt I am integrating with this, and then at into dt I am integrating with this, right? Yeah, I am now going to write it is s minus 0 is nothing but s. U is constant. U is constant. Why I am saying u is constant? Because initial velocity is constant one. It is not going to vary. What is the variable here? Whatever will be after the d, that will be the variable. Here is there is any variable with regarding to dt? Here is there is any variable with regarding to dt? Until and unless there will be any variable with respect to anything after the d, then we should have to consider everything as constant. As here there is no t, this u will be considered as constant. I am just writing it as u. What is the integrating of dt? After integration of dt I will get t, lower limit, upper limit is t, at, a is constant, I am bringing out, u is constant, I am bringing out of the integration, integral of t into dt, so integral of x power n is equal to nx. See, integral of x power n dx is equal to nx. No, it is x power n plus 1 by n plus 1. In the differential, x power n dx is equal to x to nx power n minus 1. But in integration, integral of x power n dx is equal to x power n plus 1 upon n plus 1. So here, as it is t into dt, so I am writing here t power n into dt. So it is t power n plus 1 upon n plus 1. So here n is nothing but 1. Here 2 1. So it is t square upon 2. Here t square upon 2. Then you can see how after integrating the t into dt, I am getting it as t square by 2. So it is a t square by 2. And what is the lower limit? It is 0, and it is the upper limit. We should have to write it in the bracket. Yeah. So I am removing this one. So you can see here, what I am doing is that now s is equal to u into t minus 0, upper limit minus lower limit, plus a into, you can see here, I am just bringing this 2 outside. Why I am bringing this 2 outside? It is a constant. I am just bringing from the different, I am bringing from this bracket, I am bringing this 2 from the bracket out, right? So you can see here it is inside t square, then upper limit t square minus lower limit is 0. So t square minus 0. So s is equal to u into t ut, u into 0 0 plus at square by 2 minus a into 0 0. So I am getting one more equation, s is equal to ut plus half at square. It is my second kinematic equation. You can see here s is equal to ut plus half at square. So you can see the relation between the distance, time, acceleration, between the displacement in a straight line motion. Distance will be equal to displacement. So displacement is equal to, you can see here, between the relation between the time and the acceleration, and you can also see the initial velocity too in this equation. So s is equal to ut plus half at square is the second kinematic equation. Now I am going to derive the third relation. Velocity and displacement. What? Velocity and displacement relation. So velocity and displacement. So while writing the velocity and displacement, I have a straight formula. Velocity is equal to displacement upon time. Velocity is equal to change in position upon change in time. But here there is no acceleration. I should have to take at least one parameter as a constant one. So what I am doing is that I am taking the constant acceleration. A is equal to dv upon dt. I am straightly writing here because in the previous one I told how I am writing A is equal to dv upon dt, because at a particular instant I am finding out the acceleration. So at a particular instant, if I am finding out the acceleration, then A is equal to dv upon dt. We shall have to take the integration too. But here I am finding the velocity and displacement relation. As I am finding the velocity and displacement relation, I should have to bring here displacement. How to bring the displacement here? What I am doing is that I am just multiplying by ds and dividing by ds. I am just multiplying by ds and dividing by ds. Why I am doing so? You would have seen in the first relation, velocity and time relation, velocity is equal to the acceleration. Acceleration is equal to change in velocity upon change in time. You can see here. So while finding the velocity and time relation, you would have seen the differential symbols. So whenever I am taking the relation, you can have a clue. You can have a trick. That means whatever we are finding, it should be in the D form. It should be in the differentiation form. Right. So as I am not having the differentiation form of position, that is differentiation form of displacement, so I am multiplying and dividing by ds. Is there is any wrong I am doing? No. If I am writing a ds by ds, when I am cancel out, it will become as 1, and A is equal to dv upon dt. I am just going to change the position now. So dv upon ds into ds upon dt. So now you can see it is the velocity and displacement relation, dv upon ds into ds upon dt. So dv upon ds and ds upon dt is nothing but v. Velocity is equal to ds upon dt. So it is v and it is a. I am just bringing this ds here. So dv dot v, right? dv dot v is equal to a dot ds. Now I am going to integrate. It is the velocity and displacement relation. That means we should have to integrate with respect to velocity and with respect to displacement. So here, with respect to velocity, initial velocity u, final velocity v, initial displacement 0, final displacement s. Right? Okay. So dv dot v is nothing but v square upon 2. For example, in the previous we seen d dot dt is equal to t square by 2. Like the same, v dot dv is equal to v square by 2. So I am writing here v square by 2 is equal to, this a is constant, I am just bringing this a out. And integration of ds is nothing but s. Right? And integration of ds is nothing but s. And what is the limit here? It is u and it is v. It is u and it is v. And it is a and it is s. What is the limit? 0 to s. I am just writing here upper limit minus lower limit. Upper limit is v. So v square by 2 minus lower limit is u. That means u square by 2. Whatever be the limit, we should have to substitute instead of variables. Here it is the variable v. I am having the upper limit as v. So I am substituting this variable instead of v. I am having the variable here u. So I have to substitute the u instead of v. So I am substituting here minus u square by 2, upper limit minus lower limit. As I told already in the previous one too, what we can do is that we can remove this 2 out. In the next step too, we can do this one. What I can do is that I can take the common, because 2 is common in both this one. Then I can take the 2 as common, 1 by 2 into v square minus u square. I can write like this, but it is very shortcut. What we can do is that as it is a constant, we can write this constant outside, 1 by 2. So what I am doing is that I should have to write now 1 by 2 outside is equal to it is a s minus 0. It is the upper limit. A lower limit is 0, so I am substituting here s minus 0. Then it is v square upon 2. That means v square minus u square is equal to a into s. V square minus u square into half is equal to as. And as it is 2 is present here, it is in the denominator. So while going here, after equal to, it will be in the numerator. So v square minus u square is equal to 2as, and it is the third kinematic equation which we derived in this lecture. What we derived? v square minus u square is equal to 2as, and it is the third kinematic equation, right? And it is the relation between the velocity and the displacement, velocity and the displacement relation. So we have three equations right now. I am going to write down one by one now. I am just going to write down one by one. You can see here, my first relation is that v is equal to u plus at. My second equation, s is equal to ut plus half at square. It is the displacement and time relation. It is the velocity and time relation. And my third equation is that v square minus u square is equal to 2as. It is my third relation. So I'm just taking my first two equations. Just see what I'm going to do is that s is equal to ut plus half at square. Right? It is my second kinematic equation. So I can write this equation as ut plus half at dot t. So you can see here, t dot t is nothing but t square, because if the base is same, then we can add the powers. A power m into a power n is equal to a power m plus n. We can add the powers if the bases are same. Here the bases are same, then we can write it as t square, and I can write like this too, t dot d. I can write, right? So it is also correct. So I am writing like this. Then ut plus half, instead of at, what I can write from the first one, you can see here, v minus u is equal to at. I can write like this, v minus u is equal to at. So I can write, instead of at, I can write v minus u into t. As you can see here, v minus u into t. So as it is in the addition form, we should have to equalize this one. So what I am going to do is that I am going to multiply by 2 and divide by 2 this one. I am going to multiply this ut and divide by 2, multiplying by 2 and dividing by 2, so that my LCM will come, so that my denominator will get equalized, right? So it is 2ut plus v into t minus u into t is nothing but ut, and my denominator is same, so I am writing it as 2. I equalize the denominator by multiplying by 2 and dividing by 2. So it is 2ut upon 2. So 2 same, so I wrote here 2, and it is 2ut plus v into t vt minus u into t ut. So from 2ut, 1 ut is going out. It is getting cancelled here. It is getting subtracted here. So it is ut plus vt upon 2, and I am just taking this t outside. Then it is v plus u by 2, and it is the one more equation I got by combining the first and the second kinematic equation. S is equal to v plus u by 2 into t. S is equal to, my fourth kinematic equation is S is equal to v plus u by 2 into t, and this is the four kinematic equations which we derived in this lecture. So it is the four kinematic equations. Until the force is coming into the picture, until the force we are going to consider, we have to remember these four kinematic equations, because in kinematics these four kinematic equations are very, very important. By using these four kinematic equations, we will solve so many problems. It is a basic one. If you know this one, then you can answer any problem and you will not feel any difficulty too while solving the questions. You should have to remember these four kinematic equations. So once again, what are those four kinematic equations? V is equal to u plus at, S is equal to ut plus half at square, b square minus u square is equal to 2as, and S is equal to v plus u upon 2 into t. Right? Okay. So in this lecture we derived all the kinematic equations. So just keep moving ahead and do good. And focus on your future, focus on your success, focus on your goal. Don't deviate anywhere else. So keep moving ahead and think only about your success, my dear friends. Only about your success. Don't think anything else. You don't have anything else except than reading. Right? So keep moving ahead. Do best, all the best. And if you like this video, then subscribe it, like it, comment it, and share it with your friends. So all the best. Take care.